Good morning, everyone. It's great to be here. Imagine a world where we can eliminate 10% of our global energy emissions just by revolutionizing HVAC systems. My name is Caitlin Ripley, and I'm here to tell you about an electrochemical technology that can do just that. But first, we're all familiar with our global energy emissions crisis. But today, we're just going to focus on the building sector alone, which account for 24% of all these emissions. Further, nearly half of these emissions come from the HVAC sector. And so why is HVAC so energy intensive? Well, we can look at a sample commercial system where we're feeding a fresh air stream into a building full of people. These people are living and breathing and emitting CO2 as they do that. But we need to ensure that the CO2 concentration remains below 1,000 ppm. In order to do that, we use this fresh air stream in order to dilute the CO2 in the room. Now, as we feed this fresh air stream into the room, it's going to be incredibly cold or incredibly hot, depending on the time of year, meaning we need to use a chiller or a boiler in order to treat that temperature to get it to room temperature. In doing this, we're using a ton of energy, thus emitting large amounts of CO2. And so this seemed like it was a problem that was inherently associated with HVAC systems today. And so how do we revolutionize them? Well, we can use this inline HVAC system that allows us to remove CO2 from the stale air stream that's leaving the room full of people. As we remove this CO2, we can then return a fresh air stream back into our original feed that's already at ambient conditions. In doing this, we don't need to treat nearly as much of our fresh air, reducing the volume and lowering our energy requirements. Now, this is a technology that hasn't been employed for commercial buildings like this, but we do use a similar CO2 removal device in, say, submarines, where we need to remove CO2 from the cabin air. Now, we can focus on the impact that this may have by looking at a large office building consisting of 1,000 occupants. They breathe CO2 out at a rate of 40 grams per hour, and we need an airflow of 40,000 cubic meters per hour in order to maintain the CO2 concentrations below 1,000 ppm. What this results in is a wide distribution of energy requirements depending on the outdoor temperature. So what you can take away from this figure is that incredibly low and incredibly high temperatures will require a large amount of energy. But if we were to use our CO2 air purification unit, we could reduce these energy requirements by 93 to 99%. That's incredibly large. And we can also reduce our CO2 requirements as well as the costs associated with these energetics. And so I mentioned this is going to be an electrochemical device. And so what is that electrochemical device? Well, what I propose is using a redox active capture molecule that, upon reduction, will exhibit a strong affinity towards CO2. Meaning, if we feed a stale air stream that's rich in CO2 into our device, we can capture CO2, store it in solution, and allow a pure nitrogen and oxygen stream to return back into the room. Now, every electrochemical device needs an anode or a counter electrode. And so what we propose using is a novel energy storage device coupled with this CO2 removal. Why can't we store electricity while also removing CO2? This will allow us to save a lot on money, energy, et cetera. I've shown here a stationary electrode, but what if we could also use a flowing system? This looks reminiscent of, say, a redox flow battery, where we can decouple the power and energy requirements in the system. We're able to store more energy, and why couldn't we employ this on the CO2 separating side as well? Now, we have a finite amount of our redox active capture species in solution, and so we need to regenerate it somehow. When we reoxidize our species, it allows us to release the CO2 in a concentrated stream for use in conversion to fuels and chemicals or for sequestration. This really depends on the need and our applications here. Now, once again, we can discharge our battery, sending electricity either to the grid or more likely for use in our own building. All of these two processes combined allow for us to hopefully eliminate 10% of all energy emissions. But we need to do them separately. So process one, our charging step, we can employ this during the day when the sun is shining and when people are in the office building breathing out CO2. This allows us to remove the CO2 while also storing electricity for later. At night, when people go home, they're no longer in the office living and breathing. We don't need to remove CO2. So what if we just discharge our battery at a time when we need that electricity? And so with that, I'm really excited about this prospect of revolutionizing HVAC systems. And if you are as well, please feel free to reach out and chat with me more. Thank you. Thank you.